Hi, good afternoon, everyone. My name's Laura Knight, and I'm one of the Employer Partnerships Development Managers here at Staffordshire University. I'd like to welcome you all to our AI Masterclass this afternoon, where we'll be talking about neural networks. And I'm going to introduce my colleague, Dr. Derek Colley, who can talk about this in far better detail than I can. So hi, Derek.
Hi, Laura. Thanks very much for inviting me. Right. Shall we proceed without further ado?
Yes, sorry.
Don't worry. Yeah, of course. I was panicking that my mic was off. That was all.
That's okay.
We're technological wizards that we are. We can't get webinars and Teams right sometimes. So, all right. Thank you very much, everyone, for joining, and I hope that you find the session interesting. That you get some value and some ideas from it. So, a quick obligatory vanity slide. Unfortunately, I'm Derek Colley. I'm attached to Staffordshire University. I specialise mostly in data. Anything data is me. So data engineering, architecture, consultancy, and along with data comes a certain amount of proficiency with machine learning methods and tools, particularly when we integrate them into the BI pipeline. And what that means is trying to get value out of machine learning and artificial intelligence for businesses and organisations. So with that in mind, alongside my academic interests, I'm actually an active industry professional, so I'm not just an academic. I've got around 15 years experience in this area, probably around 40 or 50 clients, ranging everyone and everywhere from UK Home Office through to small to medium-sized enterprises. My expertise tends to revolve around relational database administration, performance tuning, and data science. So if you want to know a little bit more about me, I've got a modest little website down there, or you can just drop me an email. Be happy to answer any questions that you have. So what I'd like to do in this session is go through quite a few topics, and I've structured them in this format you can see here, where we're going to have some kind of introductory material where we talk about what a brain is, and more importantly, what an artificial brain could look like. And then we're going to cover some of the sort of elementary sort of components of an artificial brain that we call perceptrons, and how they link together, how we build them, how we join them up, how we adjust them, how we make them fit for the purpose that we want to use them for. And then from there, we're going to go into a bit more detailed work around particularly around building classical computing logic gates with neural networks, the difference between supervised and unsupervised learning. The most complicated bit here really is we're going to talk about something called gradient descent, backpropagation, and weighting the perceptrons. So hopefully I'm not going to lose too many of you at that point. Don't feel overwhelmed by the mathematics, because it's really the ideas that I want you to take away from this. Then we're going to look at kind of expert level neural networks. So I'm going to introduce you to Hopfield networks and Boltzmann machines, self-organising maps, and then we're going to turn everything that you've just learned on its head and talk about recurrent neural networks, which are a completely different model from the convolutional neural network that we will have discussed to that point. We'll have a quick chat about optimization functions, confusion matrices, and then a cool down period where let's bring this back to the real world. We'll talk about how we use ANNs, how we combine them, what kind of thing we can use them for in the industrial and commercial world. And then we'll talk about next steps and where we're going towards true artificial intelligence. Then at that point, I think we'll deal with some questions and answers. So if you're all still here, then I'm very encouraged. So let's make a proper start. So on this slide here, you can see a neuron, a real neuron, a biological neuron in your head today. On the left-hand side, I mean, this diagram might be familiar to some of you already, but on the left-hand side, what we've got is a collection of synapses, and at the edge of the synapses, you've got dendrites, and the whole point of the inputs to the synapse is it takes some kind of input, so maybe a visual marker that you see, a patch of light, a photon hits the back of your retina, it fires some kind of response, that response enters a neuron, the neuron then gets translated through the visual cortex and into an image through a very long and complicated set of interactions. But what I want you to take from this is that we've got this whole range of inputs that we might label input 1, input 2, input 3, all these edges of the dendrites on the left, and then we have this kind of transmission layer. goes from dendrite through to the terminals. Now on the right hand side, we've got these axons, which are our terminals, and these are our outputs. So I've labeled these Y1, Y2 through to Ym. And what we've got here is a range of inputs, something magic happens in the middle, and a range of outputs. And that magic is still very much under the remit of neuroscience, and we understand quite a bit of what happens. But the magic of the brain is that we have billions and billions of these neurons, and neurons are created and destroyed all the time. They're kind of self-organizing. We create new memories. As I'm speaking to you now, you know, the audio you're hearing is just simply sound waves being translated through the inputs, through a whole bunch of neurons, and into some outputs that you recognize as English. So we try to emulate this in computer science by building what we call a perceptron, and a perceptron is an artificial neuron. So it models the same kind of methodology as a neuron. So on the left-hand side, we have a range of inputs. And again, you can visualize these as maybe photons hitting the back of the retina. But these inputs in computer science, we can define as perhaps a numeric value. So if we looked at, let's say, brightness or contrast, we might say, okay, we've got this neuron, we've got this visual input, it can have brightness 0 through to brightness 1, or anywhere on that range. So maybe it's brightness 0.8, and that 0.8 we can feed in as an individual numeric into our model. So if you think of not just one input, but tens of inputs or hundreds of inputs or thousands of inputs, and here on the diagram we've just got 3 inputs. The next thing we can do is modify those inputs, and we can modify them using a weight, and a weight is simply a mathematical modifier. So if you've got an input of 0.5 and your weight is 0.1, then you might choose to multiply them together, and your output would be 0.05. And you can have a different weight for every input, and you can establish one weight to have multiple inputs, or you can have a whole pile of weights, and you can have biases and things we'll talk about a bit later on. So once we've modified our inputs, we take our input, we modify it in some way, and that's our translation over here on this, what they're calling a myelinated axon trunk. I wish I knew what that was, but it's a translation layer. Then we do something with it, and in the most basic form of the perceptron, it's a weighted sum. So we multiply I1 by W1, multiply I2 by W2, multiply I3 by W3. We add them all up, and that's our weighted sum. And then on the right-hand side, we have something called an activation function. And that's really just a rule. That says if the weighted sum is greater than X, then produce this number. Or if it's less than X, then produce this number. Or it might be a bit more nuanced, and we'll see that in the next slide. So this is a kind of worked example, and I'm going to just flick over to Excel, not to scare you with too many numbers at this point, but a worked example of how a single perceptron can work. So on the left-hand side here, we've got 3, 7, and 8 as decimal inputs, and I've set the weights at 0.1, 1.2, and 0.8. So we've got a weighted sum because we multiply each input by its weight. Then we add them all up, and we get to 15.1. So far, so easy. And then we've got an activation function, which is something called a shifted Heaviside step function, but in reality, it's just an if statement. It says if the weighted sum is greater than some threshold, then 1 or 0, and then we get an output 1. And that's a really, really simple rule. And the wonderful thing about this is I want you to try and visualize cycling through lots of different inputs. So instead of just having 3, 7, 8, maybe we feed it 1, 2, 1, or 0, 4, 6, or 2, 4, 8. And then we can see what comes out of the other end. And the difference here is that we've built what we call a non-linear function. And I just want to flip over to PowerPoint to a blank kind of presentation to give you an idea of what that actually means. So we've got in a normal function, so we've got some input I like this, okay, and in a normal function, which I'll draw as a little black box here, function here, and then we've got some output here, okay. Now let's say a function was defined as +2. So anything that comes into this black box, we add 2 to it, and we get an output. So if I equals 1, we add 2, and O equals 3. If I equals 6, we add 2, and O equals 8. So this is what we call a linear function. And the reason it's called a linear function is because if I took every possible input and tried to graph it over here, and you have to excuse my terrible drawing, I might find that my graph looks a bit like this, straight line going up. And this would be 2, 3, 4, and so on, 1, 2, 3, 4. And the rule is basically y equals x plus 2. So we've got a nice linear function. Now, the difference between a linear function and a non-linear function is that we might have a function here, which has lots of inputs. And how do we define that? So we might have I1, I2, I3, I100, and then we'll have an output. So now we need to define what that function is. And our graph for that function might not look like a straight line. It might look something like this, or it might look something like this, sigmoid function, or anything at all. It might be completely wild and variable. It might look like that. Okay, so that gives us a bit of an advantage and a disadvantage, because it means that our advantage is we can make our function, which is really our artificial neural network, as complicated or as simple as we need it to be to fit the data coming in. But the downside is it can be a little bit complicated to compute the weights. And if I just flip over to Excel briefly, so what we've got is that exact example that I just gave you just now. So we've got 3, 7, and 8 as inputs, A, B, and C. I've got my weight set up as per the PowerPoint presentation, calculate the weighted sum, get our activation. And what I've done here is create something called a confusion matrix, which I'll cover later on. And the important thing here is that I've established my model, given all these training inputs here and desired outputs, is around 16% accurate, which isn't great. I've computed something called the mean squared error. So what I've done here is I've adjusted all these weights. And if you can see where I'm highlighting, I've adjusted all these weights. So weight A has gone up from 0.1 to 0.9, B from 1.2 to 1.8, and C from 0.8 to 1.5. And what I've done here is make my model more accurate, because I've now got a far higher critical success index, which is one way of measuring how accurate a model is. And I've also got a lower error. And we'll talk about what errors mean soon. So here what I've done is I've created a non-linear function. Okay, I've fed it some weights, I've looked at the output, I've observed the output, then I've adjusted my model, A, B, and C, all my weights here, and then I've put in the input again, same set of input, and I've realized that my model is slightly more accurate. And I can keep doing this again and again and again to try and bring that error down to 0. And what I've done there is create a nonlinear function using trial and error, using an ANN. So let's move on. A perceptron then sounds incredibly complicated, and it's not. Okay, this diagram on the right hand side, anyone can write a perceptron. Once you get the general hang of the idea, you can write it in any language you want. And I wrote this one in C#. So all this is, we're declaring some variables, 3 inputs, 3 weights, and all we're doing is calculating a weighted sum, and I've got a Heaviside step function in there as well. So not a great deal of code. The difficulty here is building these perceptrons in a way that they can connect to one another. That they can form networks, that instead of having to go and adjust the weights manually in Excel, as I'm doing here, and trial and error and doing a lot of hand calculation, we can do this automatically. Okay, so we can take a weight adjustment, calculate what that weight adjustment should be based on the error, and work backwards through our neural network. So hopefully that's fairly clear. I just want to talk about the activation function. I keep using this term Heaviside step function. All the activation function is a way of turning or normalizing the weighted sum into some output. Okay, so we've got a weighted sum. We multiply everything and add everything up, and we say we need a rule that produces an output based on what that weighted sum might be. And the step function is really straightforward. It's named after a chap called Heaviside, I think back in the 1920s. Maybe that's maybe even earlier, in fact. And the typical Heaviside step function is a really simple if rule. So if the input is less than or equal to 0, then output 0, else output 1. So the function graph looks like this, dead easy. But we've also got other sorts of activation function called the sigmoid function, and that's the one on the right-hand side. And as you can see here, if I feed it a weighted sum of 1, then my output would be about 0.75. And there are many, many, many types of activation function I could use. Here's just 2 of the simpler ones. What this does mean is hand calculating this can get a bit complicated, because when we're trying to work out how to adjust the weights, if we're using a step function, it's quite simple. But if we're using a continuous function like the sigmoid, it can be quite difficult. So let's talk briefly about how we can join these perceptrons up. When we build an ANN, I want you to now sort of step away from this diagram here and imagine that everything over here, this entire diagram on the left-hand side, is encapsulated in one big circle. Okay, so this circle is a perceptron, and this circle takes inputs and has outputs. Okay, so from now on in, every circle you see, I want you to think of as a perceptron. So on the right-hand side, we've got an example here, and this is a real artificial neural network that's trained to recognize numbers above binary 4. Okay, So we might need that as, it's a very, very simple kind of idea, but we might need that as a kind of some small component of a wider machine learning platform. So maybe we're doing some sales forecasting and we want our artificial neural network to trigger when a particular number, a particular quantity of sales or product quality estimate or anything at all reaches some certain value. And this might be one way we can train it. So here we've got this output value giving us a decimal input, 4-bit binary, and we can see that the output is simply a function that goes up. So by doing this, I mean, we can wire together these perceptrons, and we can establish, when we wire them together, we can establish the weights between them. And we create layers, and typically an ANN will have an input layer, one or more hidden layers, and an output layer. So the weights are always illustrated as numbers on the connecting line between those. So we are going from some input to some output via a weight. Okay, so it's a directed graph. The output layer combines all remaining outputs to a final output figure. And in our example, we've just got one perceptron in this layer because we just want one output, and we can have any configuration we want. What you're looking at here is something called a convolutional neural network, also called a feed-forward neural network. And it's called feed-forward because we start from the left, and it was good timing for my animated GIF. We start from the left and we can progress through to the right. So your inputs come in here. And again, think of these as binary digits or visual inputs or sound or anything that you want. And then we progress through to the hidden nodes here and then out to the output. And the reason they're called hidden nodes is because there's no direct input from external stimuli. So if you think about the brain, if you had some neurons which were connected somehow to the retina via the optic nerve, and they receive some kind of light information, some kind of photon hit, some kind of firing mechanism, then a hidden neuron might be something that sits behind that translates that image into something that we can recognize from our memory. So this whole structure, whenever we wire these perceptrons together, we move from this idea of a single perceptron to an artificial neural network. Okay, and a neural network is simply a collection of perceptrons that have been wired together in some form or another. So unfortunately, it does get slightly more complicated than this. So we can, I'm going to move into the kind of detailed work now. So we can have perceptrons which aren't simply the ones that we're used to, our input ones, our hidden ones, our output ones, but we can influence our models by adding some kind of bias or adding some kind of context, which can be a very powerful technique. So on the left-hand side here, I've already defined these hidden perceptrons. They only accept the outputs of other perceptrons, and their outputs are only used by other perceptrons, so they're completely invisible to the outside world. But then we can have these bias perceptrons as well, and that might be that we want to bias the output of our model in some way. So for example, if we're building an artificial neural network to do sales forecasting, and we know, for example, that we're expecting an uplift in sales due to, could be anything, maybe the time of the year or a new store opening or a change of policy or some new products coming online, then we might find that our models don't necessarily fit all the information that we have to hand. And we can add bias to our models to adjust the output by some amount. So all we're doing is really shifting the output of the model left or right. If I give you a better example, because that's really a terrible one, I did a piece of work on sentiment analysis recently against Amazon product reviews, and what I was trying to build was a model that would read through several billion Amazon product reviews, and I wanted to extract all the words that were used in those reviews and build a lexicon. And using that lexicon, I could take a completely different data set, like maybe Twitter tweets, feed it into my model, and I could establish whether a tweet was positive or negative, which might be useful for a company who's trying to handle brand reputation. And it was successful, it worked. But one problem I had was that the Amazon review data was skewed to the positive. I'm not going to speculate on why. But the fact of the matter is that these reviews are not evenly balanced. So I didn't have an equal number of negative and positive ones. So I had this kind of skew, and I could correct that skew by adding bias to my model to de-skew it and bring it back to the median, which is what I ended up doing. So a fairly long example, but hopefully you can see the kind of merit of adding bias when we need to. And a bias neuron is an independent neuron that simply adds an additional input into some other perceptron in our model. And then we really get into an interesting concept, which we'll come back to when we look at recurrent neural networks, and that's this concept of context neurons. And a context neuron is quite a magical thing because it's a memory. It essentially allows you to add some context to the calculation of a neuron's output. So you can say, hey, last time we got 0.5. So this time I want you to factor the last result into this model. So we're going to use, if you think about a neural network as something that changes over slices of time, so 0.1, 0.2, 0.3, 0.4, we can go back and use something that happened in 0.3 to influence 0.4, which is not something we can do with a normal model. And context neurons act as a short-term memory, and they form the basis, in fact, for recurrent neural networks and something confusingly called long short-term memory modeling. So, again, I hope I've still got everybody. So what can we do with these? So far, these are very abstract, very academic. We can build logic gates, and if you have any kind of background in computer science, you might vaguely remember this whole concept of having and or not, exclusive or, and so on. These kind of gates that we can build where we have some inputs, and based on the inputs, we can determine an output. So it's a linear function, really. So an AND gate would say that if I have input 1 is positive and input 2 is positive, then my output is positive. In every other case, it would be negative. So, if one of those 2 is 0, then it's negative. So think about 2 keys for the nuclear missiles, okay? If I have both keys in the slot and I turn both keys, I've got 2 inputs, which are both positive, and then my output is I fire the missile. If I've only got 1 key, no missile. If I've got no keys, no missile. Okay, so these gates are really the fundamental building blocks of computer science and Boolean logic. And we can build these gates, as you can see from this GIF on the top right, from neural networks. So if we go and set our neural network weights in the way that we see here, and we're using a bias neuron to help out, then we can get a firm output. And that means that we can build, thanks to Alan Turing, who kind of proved this, if we can build the logic gates, and we can build a Turing machine, and if we can build a Turing machine, then we can build any computer imaginable. Okay, and that can all be built from ANNs. So we know that ANNs are universal in nature. The wonderful thing as well is that we can build any kind of logic gate using just NANs or just NORs, which are a couple of discoveries from Sheffer and Pierce. We can use the gates to build software tools, and we can chain those gates together and introduce logical operators and conditional branching into our code should we want to. Really great book to read, by the way. If you do manage to get hold of it, it can be a bit rare to find, but you might find it on Amazon. Jeff Heaton wrote a really interesting series. I think it's up to 5 volumes now on ANN. So there's a reference just on the bottom right of the slide there, and hopefully we can share these slides around. So far, we've got as far as building an ANN, and I want to just very briefly differentiate between supervised and unsupervised learning. So an ANN is a machine learning model. It's not the only kind of machine learning model out there. We can, for example, classify data by clustering. We can use association rule mining. We can do lots of different things in AI, linear regression and so on. But all of those techniques can be broadly classified into supervised or unsupervised. And supervised is where we have a set of data with outputs that we want, and we feed it into our model, and then we take a set of data that we don't know what output, well, we know what outputs we want, but we don't know what we're going to get, and we feed that data back in and see what happens. So we have a kind of training set. So we say, okay, here's pictures of animals, pictures of cats or dogs, okay? So I'm going to expose my ANN to all these millions of pictures of cats and dogs, and then I'm going to give it a picture of a cat and say, what is it? And hopefully my ANN will come back and say, that's a cat, rather than a dog or a llama or a bird, to a high degree of confidence. And the way that we can use that in industry and commerce is we can apply ANNs to things like quality control mechanisms. We can look at plants, we can look at machinery or fleet or anything that you physically manage, and we can say, okay, how often does it break down? What's the throughput rate? How old is the machine? Can we make a prediction of when it will next need maintenance? How reliable is it? Can we score that as a risk? So we can do lots and lots of different things, but it does rely, the supervised method, on having that data beforehand that you prepare, you feed into your model, you show your model what the thing is that we want to do, and then hopefully it does it to a good degree. So the whole kind of process is illustrated in this diagram here. So we train an ANN with unsupervised learning. So we give it a table of data, and then for each set of inputs, we train our model. And there's a couple of ways we can do that, online or batch learning. And our model looks like this complicated squiggly diagram in the middle. And then out of that we get an error, and this horrible little equation here simply means what's the difference between what we expected and what actually happened. Okay, if I flick back to Excel, this is a really simplified version, but here I've got an error which I've calculated as 5. So there's 5 out of 10 here results that didn't go the way I wanted them to go. Okay, and by adjusting the weights, there's now 4, so I've increased the accuracy. And again, it can get a bit more complicated that depending on your error function, but that's the general idea. What happened versus what I expected to happen. Now, start getting a bit more complicated. When we want to adjust our weights, you can see it would be incredibly hard to do this by hand, one after another. So what we're really looking to do is try to in back propagation, which is an example of something called gradient descent, what we're trying to do is adjust our weights towards the state where we've got the lowest error coming out of the model. So if I flick back to this slide here, what I'd like to do is continue to feed training data into my model and adjust all of these weights incrementally, adjust them in such a way that my overall error, that's my difference between what I want to happen and what actually happened, decreases to an absolute minimum. Ideally 0. If it's 0, it's completely accurate and we've built ourselves a universal machine that can predict anything. But in reality, we're going to try and bring it down to a minimum. So this model should be as accurate as possible all the time. That's what we're aiming to do. And that's what gradient descent means. So here on the diagram, we've got a single gradient, we've got a single weight, which we adjust over time and it descends towards a minimum error. And the minimum error rate is a really good way of determining the accuracy of a model. The lower the error, the more accurate the model. There's a couple of ways we can do it. We can use something called stochastic gradient descent, and that word stochastic will turn up more and more often as I go through these slides, and it means random. That's all it means, randomness. So we can have random gradient descent, so we progress in a kind of zigzag fashion towards our minimum error, or we can have a smooth gradient descent, so which can take a bit longer, but can be as accurate. So the idea is to adjust each of those weights to a point that the overall error is reduced. But this gets a bit more complicated, okay, because unfortunately, we've not just got one weight, we've got lots of weights, and then we've got lots of layers of weights. So we've got to work out how each weight contributes to the overall error per layer. And unfortunately here, we have to go into calculus, okay, which is why we've got some scary looking equations on the screen. So what we want to do, the whole point here, and this horrible looking equation means to calculate a new weight, we need to calculate the old weight plus some delta, plus some difference. Okay, and that can be negative, so it might be minus some difference. So if we've got a weight of 0.8 as our old weight, and we need to calculate what it should be, then we're going to add or subtract something from 0.8 to achieve that. And the mechanism for doing it is this horrible looking thing over here. And this means the delta of W is the differential between the error rate in respect to the weight over the differential of the weight multiplied by the learning rate in a negative direction. And if you think that sounds absolutely awful, you would be right. I'm going to hopefully bravely attempt to, let's get a new slide. Let's do differentiation in 10 seconds, I hope. Should have added more blank slides, just bear with me. Right, so when we differentiate, all we're really saying is we want dx over dy, okay? And all d means is a bit of. And what it really means is a little bit of. And what we're really asking is what is the ratio of change between x and y? So the way it was explained to me a long time ago, which I really like, is imagine a ladder. Okay, this isn't a graph, it's a ladder. Chap here with the ladder, right? So he pulls the ladder, this is x and this is y. He pulls the ladder towards him. What happens to the top of the ladder? It goes down, okay? If he pushes the ladder away from him, top of the ladder will go up. So we can say that there's going to be a difference in the distance that the bottom of this ladder moves between here and here, and there's going to be a difference in the distance that the top of this ladder moves between here and here. So what is a ratio of x to y? Okay, given any distance of x, how will y change? We can express this as a ratio. So it might well be that if we move the bottom of the ladder out by a foot, then the top of the ladder moves down by half a foot, depending on the angle of the ladder. So here we can say 1 over 0.5, okay, which is really 2. So here all we're doing is working out what this ratio is, and the trick of differentiation is to say for any distance, x and y, for an infinitesimally small distance, okay, what we're trying to do is get something called the instantaneous gradient. What we're going to say is for any distance whatsoever between x and y, what's the ratio? So for any bit of x, what's the ratio? Okay, that's differentiation. That's all it is. And I wish somebody had told me that when I was about 15, because I would have got better marks in my exams. But that's all differentiation is. So that's what we're looking to do here. We're taking the error rate. Okay, that's our x. And we say, okay, the error rate in respect to the weight over the weight. Okay, what is the difference? How does adjusting a weight affect the overall error? Okay, we need to differentiate that in respect to all the weights that we have. Now, that does beg the question, what's an error? Okay, how do we define an error? Now, in my Excel spreadsheet, you saw that I defined it in a couple of ways, or a couple of very simple ways. So the first one was adding up all the differences between what I wanted to happen and what actually happened. And when I do that with ones and zeros, it's the same as something called a mean squared error. Okay, when I do it with continuous variables, it's a bit different. But a mean squared error, I take all the differences, I square them, then I add them up. Okay, that's all it is. And I've got a different measure underneath, which we'll cover a bit later on. So there's two main methods in neural networking to calculate an error. There's a mean squared error, which is this horrible looking formula over here, which again, it simply means square the differences and add them up. Okay, pardon me, square the differences, add them up and divide by the number you have. So the average of all the squared differences. And then we have the cross entropy, which is actually a bit more easy to calculate, involves a logarithm. And what we're looking here is to try and codify it and calculate the information loss between two sets of data. If you're interested in information theory, Claude Shannon. Okay, so go off and Google Claude Shannon, do a bit of reading there. It's quite a simple measure to calculate, but quite difficult to understand intuitively. I'm not going to read the slide out. Okay, this is really for reference. So here, what I've attempted to do with, I think, modest success, is walk through updating the weights of the output, going to the output node in a single layer A and N. Okay, so I've got no hidden values in here, because otherwise the calculations are going all day. I'll probably get them wrong. But we have the weights going from the input to the output, straightforward A and N. I've got 3 sets of training data here with some desired outputs, and we're going to walk through each of these operations that we need to do. So we've got all these formula calculations, bit of help online to work out the differentials versus Wolfram Alpha, and then we can step through all of the calculations. And to kind of skip to the end, we update each of the weights, and what we've managed to do is reduce our mean squared error by a very modest amount. Okay, so we had the mean squared error, it's I think 114, we've reduced it to 113. And the more data I feed into this, the lower my error will become, because the more those weights will be finely attuned to what's coming in. And this whole process is called backpropagation. Okay, it can be quite complicated, it does involve the calculus, but it's fairly well understood, and there are alternatives out there to this. One of the problems with backpropagation is that if you've got a function, or if you've got data that looks wobbly like this, then you can get stuck in a valley. Okay, because we're always descending down the gradient trying to find a minimum error, we might find that we've got, if I can just reuse this, we might find that we've got, you know, data that looks a bit like this. And we can find that our minimum point might actually be here. That's the lowest possible error that we're aiming for, but we get stuck in this valley here, which is actually a bit higher. Okay, so we get stuck in this valley, and this is called a local minima. And unfortunately, backpropagation is incredibly good at getting stuck in this local minima. Think of a marble, okay, that's attacking this model here. It's got a certain amount of energy. It comes in, and it's going to get stuck here, and it's never going to progress over this next valley, given enough kinetic energy. Same idea. All right, so backpropagation isn't ideal all the time, but it's a well understood model, and it can work quite well. There's a couple of bits of terminology here that I want to introduce as well. So in online training, we modify the weights after every input vector. What does that mean? So every set of inputs, you know, I1, I2, I3, we run them, then we modify the weights. Then we run another one, then we modify the weights. Then we run another one, and we modify the weights. in batch training, we sum all the gradients for every input vector and then apply weight changes at the end. So we apply a kind of average to the whole thing. Or what we might do is run multiple epochs, and an epoch is a whole set of training data, then adjust the weights layer by layer. Okay, and we can train the model again and again in multiple epochs. So still a quick time check. I think we're doing okay. Right, so recurrent neural networks. What we've covered so far is a convolutional neural network. That's feed forward, left to right. So I want you to kind of bear that in mind, put that to one side, and start thinking about how else we could structure networks of perceptrons. So when we create what we call a fully connected neural network, or a partially connected neural network, where we start mixing up this idea of just having a feed forward neural network, and we can maybe connect the hidden neurons to each other or back to our inputs in some new way, or introduce memory, then we start to get somewhere quite exciting in terms of how accurate these models can be. They do become a bit more complicated. So there's a diagram bottom left-hand side here, and this part on the left-hand side is really, it's flipped vertically, but we've got an input at the bottom, and we've got a hidden neuron here and an output. Okay, and what we've done here in our new model is we've connected the hidden input to itself. Okay, the hidden neuron to itself. The output of the hidden neuron feeds back into the input. And each of these slices here are time. Okay, so think of these as updating the weights over time. So we've got the first second, the second second, the third second. And all we're doing is adjusting the weights as we go. But because we've got many more of these connections, we get some weird and interesting behavior. And the algorithms get a bit more complicated. And I did reach out and have a look for better definitions, and I can explain at this point. And there was a great one here from IBM. And it said, well, feed-forward networks have different weights per node. Recurrent neural networks, share the same weights throughout each layer of the network, and it uses something called back propagation over time. So time becomes a definite dimension in these kind of networks. And there's a few different kind of standard models of recurrent neural network that we can look at. One I mentioned a bit earlier, which is a long short-term memory, which I'm not going to cover today, but a couple of the primary ones are Hopfield networks and Boltzmann networks, which I'm going to move on to for the next slide. So again, hideous diagram, and I apologize, but think of a Hopfield network as a fully connected neural network, and that means every single perceptron is connected to every single other perceptron. And here, hopefully, we can come back to some intuition to understand why this might be beneficial. There's a chap called Hebb in 1949. Hebbian learning is something that's sort of fundamental to education, but he did a lot of work in neuroscience as well. And he said, or he defined formally, that neurons that are physically close to one another can excite one another. Okay, so if I've got a neuron which is physically close to another in my brain that is dealing with a visual input from my visual cortex, then the neuron near it will fire also. Okay, so the way that I've seen it put, and I really like this, so it's in bold, neurons that fire together wire together. Okay, so the more interaction between neurons that are physically close to one another, the more chance they're going to build connections and form an artificial neural network. And that's really the fundamental idea of a Hopfield network. So he created in 1982, Hopfield created this Hebbian rule. He took this Hebbian rule and created this idea of a neural network. So it either fires or it doesn't fire, each neuron, this is, depending on the input it receives from other neurons. And he said, well, we can connect these two neurons using weights, as we do in feed-forward neural networks, but we also have this threshold. So, neuron times a weight, if a neuron times a weight is greater than a threshold, then increase the state of the neuron, else decrease the state of the neuron. So in other words, think about two neurons that can move. If we have one neuron firing and it fires this neuron here, they can get closer together. And if we have one neuron that fires here and this one doesn't fire, then maybe it can move further apart. And if we fire more and more information into this, we're going to get neurons that effectively build their own networks, but not moving around physically, but moving around in the mathematical space. So we have lots of clusters of neurons which will form, and we have clusters of neurons which will be distinct from that. So weight here is really a distance measure, and this was a real sort of output of Hoffield's work, that he said, because this is a self-organizing brain, essentially we can do a lot more with it than a very static feed-forward network. One of the things we can do, for example, is we can update using the inputs, we can update all the neurons randomly. So we can say, okay, update that one, then that one, then that one, then that one, and we'll see what happens. Or we can update them all together and rearrange the whole brain on every sort of flash of input. Excuse me. So Hopfield networks are really great at pattern recognition. So you can take, unlike a feed-forward neural network, you can take any amount of inputs arbitrarily. So on your first phase, you can take 5 inputs. On your second one, you can take 400. Second one, you can, third one, you can take sort of 20. And you can have any number of inputs and any number of outputs, and you can expose them to patterns repeatedly. And what you're doing is setting the network up to recognize these similar patterns in the future. Okay, you're showing the network these patterns, and like the feed-forward convolutional network, you're setting this whole kind of ball of interconnected neurons up to do the work that you want them to do. One thing that a Hopfield network has that a feed-forward neural network doesn't have is something called energy. And we can calculate the energy. The formula's horrendous, so it's not here. We can calculate the energy of a Hopfield network. And when a Hopfield network has a lot of energy, it means there's a lot of potential for change. Okay, there's a lot of potential for these neurons to get closer together or further apart, and for all the weights to adjust. And when it's in a low energy state, the Hopfield network is very stable. Okay, so our brains are in a fairly low energy state as adults because we struggle to learn new things, especially as we get older. Our brains have lower plasticity, especially as we get into older age. We start suffering from degeneration of the neurons. But it's a very young age when you're 3, 4, 5. I mean, the world's your oyster. You can learn another language. You're a sponge. You have high plasticity in your brain. So you could say that at a young age you have a high amount of energy in your brain. Okay, a high amount of Hopfield energy. And at an older age, maybe you don't have as much Hopfield energy because your brain is more stable. Same kind of idea is at work here. So there's an image shamelessly ripped from Wikipedia on the right hand side, a four neuron Hopfield network, and you can see how each of those nodes are interconnected. So you're all now familiar with Hopfield networks. So let's take a special case of the Hopfield network called a Boltzmann machine. And this was a chap called Boltzmann. He ran with this idea from the 40s and said, what if we had a fully connected Hopfield network, but we made some of the nodes hidden? So inputs could only go to some nodes rather than all of them. And we had hidden nodes as we do in a convolutional neural network. And what would happen? And he established a bit more terminology. So he found that these could be more accurate in some circumstances, that we could store more information, they're less changeable. And he defined something called a temperature of a Boltzmann machine as well. So he said, this is a probability that the total energy of my machine will change given some new input. So again, think back to the brain. The probability here could just simply be age. Okay, what's the probability that my 4-year-old is going to learn a new song, from watching the TV? Probably quite high. What's the probability that my grandmother at the age of 86 will learn a new language? Probably quite low. Okay, and it's the same kind of idea here. So we've got the whole temperature of a BM to define the probability that it's going to increase in that the total energy will change. The other thing I need to add as well that isn't necessary on this slide is that energy always decreases. Okay, you start off with a Hopfield network or a Boltzmann machine. The energy decreases as you feed more and more data into that machine until it's stable. And the whole idea is to bring the system into what Boltzmann called thermal equilibrium by running the BM with enough input. So essentially, the overall energy converges to a minimum. Okay. What I'd like to do, just for the change of looking at PowerPoint, not to death by PowerPoint, I wanted to show you this a bit earlier actually. This is a perceptron. It's a 400 cell photo array built back in I think 1930, 1940. It's called the Mark I Perceptron, built by Cornell Labs, I think, it was 1958 if I remember correctly, from my reading. So what this is all your inputs here are photo cells, so they're taking light input, and they are all connected up in the world's first artificial neural network. All these items on the right hand side here are variable resistors. So if you think back to being in school and you plug in the 2 wires into your breadboard and you've got the little resistor that you can adjust by hand to vary the voltage between A and B. That's all these are. So you can vary the voltage between one node and another, and you've got all of these resistors available. And this was really a scientific experiment to see if such a perceptron could be built. This was built by, wish I could remember the name, I will look it up. Rosenblatt, that was it, Henry Rosenblatt or Harry Rosenblatt. And he was one of the pioneers at Cornell, 1958, of these perceptrons, so building these in hardware. And what we have now, we've got, I think Harvard came up with something called NeuroGrid very recently, which is a very complex set of Boltzmann machine Hopfield network based ANNs that fit on a slice of hardware. Okay, so this kind of hardware approach is still very much active. Right, so we built a Boltzmann machine. What kind of thing can we, do? We've got a variant of the Hopfield network similar to the Boltzmann machine here, called a self-organising map. And there is one key difference between an ANN and an SOM, that they are unsupervised. Okay, what we don't give it a training set of data. We give it a stream of data and say, okay, here's all our sales figures, here's all our quality metrics, here's all our tweets, here's all our visual, video streams, or whatever it is that we want to try and train the model on. We build a grid of neurons connected by weights, which is what we're looking at here, and we say go. And essentially what happens is the grid of weights fits itself to the data that you have. So if you imagine this blue blob as data on an XY plane, okay, so it's got a coordinate system, it's got two descriptors of some kind, or maybe 3 or 4, you can have any number of dimensions. You have all of your data, and you build a network, and you point at the data, and you say, go. Map yourself to the data. And I really liked this visual, and unfortunately I haven't referenced it, which is a cardinal sin, but I really like this visual. It isn't mine. And the visual shows how a self-organising map can fit itself to the data. So the blue piece here is your data. This little dot here is where it currently is in the training. So you can see this yellow sort of splat here is pulling the network towards the dot. Okay, and over time, as you let this network sort of read the data and feed it into its own system, it will fit itself around your data. So that means that any new data that comes in that roughly corresponds to your blob is going to, you get the outputs of your neural network are going to be pretty accurate. So yeah, essentially the algorithm for doing this is really quite simple, even though it doesn't look simple at all. There's no calculus involved. It uses something called the Euclidean distance, which is simply a distance from point A to point B, and it just iterates over and over. And these kind of maps fit themselves to your model. The downside of this kind of map is if you get some data in which doesn't fit what you expect, your cluster of data here, your sales, you get a blob of blue data over here, then your map is not going to be much use in classifying it. It may even distort that data somewhat. And we see the same problem in other techniques like k-means clustering as well. Just a quick note, these were invented by a chap called Cohen in 1982. So I'm nearly at the end of the complicated bit. So confusion matrix. One question from this is, no matter how complicated or simple an ANN we build, how do we measure the success of an ANN? And a confusion matrix, also called an error matrix, is one way of doing that. And the whole idea here, if you have a look at this small table on the top right hand side, is that we can classify our responses into positives and negatives. And of those, we can classify them as true positives, false positives, true negatives, false negatives. Okay, so here we've got a number of test iterations. We've got 12. We've got the actual classification that our ANN achieved, and then we've got the predicted classification. Okay, so that's what we wanted to happen. Is that row there, and that's what actually happened. And then we can classify each of these as a false negative, true positive, true negative, false negative. Okay, so we've got these 4 kind of classifications. When we add them all up and put them into here, it's called a confusion matrix, and it's a really great visual. Now, the wonderful thing about using this kind of metric is that we've got many measures we can derive. So one of them that I used earlier in Excel, and I'll come back to it in a moment, is a critical success index. So this is defined as the number of true positives over the count of true positives, false negatives, and false positives. And that's one really good measure, a good single percentage for how well our model is performing. So there's an example on the slide here. We've got a true positive rate of 0.9. We've got some other numbers to plug in for the denominator, and we can say our model is 75% successful. If I come back to Excel, I can show you I've just calculated that here. It's really, a very simple formula. All I'm doing is just counting out the number of true positives, negatives, and so on, according to my formula. And I can see here that we've gone from an index of 16%, which is not very accurate, to 42%, which is a lot more accurate. And if I described all this on a gradient, it would look like a curve. Okay, so it's not quite as harsh as a simple, yes or no. It's a nice flattened curve. So lots of different metrics, and I encourage you to go and look those up. These can be really, really useful for establishing how good your models are. And the final bit on the complicated slides, I promise, combining these artificial neural networks is something that's called bagging. And by bagging, we take lots of different ANNs, maybe 2, 3, 4, 10 of different types perhaps, and we can take the outputs and average them. Okay, and what that gives us is a great deal more computational variation. Okay, it gives us, if our model is biased, for example, in some direction. So we've got a feed-forward neural network where we're being trapped by local minima. And then we've got a recurrent neural network where we're not having that problem, but it's very chaotic because it's got a lot of energy in it. And we've got another type of neural network. And what we can do is take those outputs and we can average the outputs. And we can take that as our overall output for the model. And by adjusting each of these individual neural networks, we can achieve a kind of output by consensus. Well, the one thing that does also allow us to do is take our input data. Imagine it's massive. Imagine it's a video stream of ones and zeros, okay? And we can divide it up into what we call feature subsets. And that means that we can take portions of our data and parallelize those operations so they can all occur in parallel, feed them through our neural networks, and then take the outputs. So that can help split the load, improve our performance, and improve the accuracy of the model. So this image here I found in a bioinformatics paper, which is referenced at the bottom, but I thought it was quite a nice, so ignore the binding affinity at the bottom, that's just peculiar to the paper, but the actual idea is pretty straightforward and I think well explained by that diagram. So what can we do with these? ANNs are uniquely suited to classification, pattern recognition, and forecasting problems. So things that they're actually used for are things like facial recognition. If you've ever had the misfortune to drive past an ANPR camera and have your number plate captured, and then you get a nasty letter and perhaps a trip to a speed awareness course, you've been caught by an ANN. ANNs have been used in the literature for things like forecasting energy output for buildings, for forecasting the amount of waste that comes out of construction projects, for looking at air travel demand predictions, there's one here for disinfection byproduct levels in tap water, it's a bit applied. And then COVID-19 cases based on prediction. So we can use ANNs to predict what would happen based on a whole pile of feature inputs. And you can see how many confounding factors there are in, for example, a COVID-19 forecast. And you can see perhaps now how ANNs can help you do that by taking all of those input features, throwing all of your training data through it. That's what's happened so far, and then making predictions based on the future. Not infallible. There are thousands and thousands and thousands and thousands of cases out there. A good place to look, if you don't mind a fair bit of reading over a cup of tea, is scholar.google.com. So have a look for anything with artificial neural network case study in it, and you will find, I think it was 90,000 results when I had a look. There's also lots of companies showcasing what they do as well. So nearly at the end, quick time check. I think we're doing okay, 7 minutes. So a bit of time for Laura to present any questions, I hope. I was going to cover something about the ethics of building an ANN, but I'm going to leave that to you to research. I mean, should we build a brain? At what point does the brain become self-aware? We're not there yet, but we are getting closer. ANNs in the meantime are useful for applied applications, particularly in commercial and industrial settings. Good news is you don't have to do any calculus yourself. You don't have to open Notepad and get going with an ANN. You can if you want. I wouldn't recommend it. There are plenty of free and open source tools to build ANNs without having to learn all the calculus. Okay, so one I would recommend if you're a complete beginner to this is PyTorch, and if you go to pytorch.org, which I have open here. It's an open source framework, so it's not a paid for tool. I'm not trying to flog you at all here. I don't have any vested interest in this. It's completely open source, which means it's free for you to use and learn. There's lots of documents, lots of resources, lots of tutorials. It's based on Python. And the idea here is that you can build your own ANNs out of the box, off the shelf. So I want a feed-forward neural network with this many inputs and this training data and so on and so forth. And you can train your models and you can integrate that into your application code, into your business workflows, into your BI, your business intelligence, into your analytics, anywhere you want. Most major tools now support some kind of ML integration. So if you're working with databases in your business, for example, you'll find that tools like Azure Data Studio can be used to interface with PyTorch. You can use the Spark framework for distributed data processing. You can write this as a part of your business logic in pretty much every major language that there is, so Java, Python, C#, whatever you like. And so there's a whole pile of information here. If you want to get started, pytorch.org, go and have a look, go and have a play. There's nothing that you'll break, and really get to grips with how that works. And I just want to play a very, very short video. There is some nice audio in the background, but I don't think this platform is unfortunately let you hear it. So I'll just talk over what you're seeing here. This was a video by Denis Dmitriev. Denis is a sort of visual expert, and I just really like the video, so I just want to play this for you. So what you're seeing here is Denis has created this these visualizations of different sorts of networks, and what they're doing is they're analyzing handwriting, so digits. And you can imagine this being used if you're doing optical character recognition, so scanning handwritten documents. And the inputs are this flat layer here, and these are all handwritten documents, and all of these are the hidden layers or the neurons involved in your neural network. So here you've got 2,000 hidden neurons. You've got a little over 1 million different weight connections between them all. And there's only 2% shown, 2% of these weights shown in this visualization. And as the video progresses, we'll see a couple of other types as well. So we've got the multi-layer perceptron model. That's a feed-forward convolutional neural network. And here you can see the hidden layers more precisely. So you've got our inputs on the left-hand side. We have our hidden layers here. You can see how well they're all connected. And our outputs are here, and you can see these dots as these handwritten digits come in. These dots indicate how they're being classified. Okay, so imagine this at scale for all symbols in the English language, and that's quite a nice visualization of how these work. I think we've just got another minute. We've got a couple of other types as well. So here we've got lots of different examples of handwriting input that have been divided down into different input neurons. And these are being done, the important bit here, they're being done in phase. Each of these flashes is a point in time where all the weights are being updated. Okay, so all of these weights are being updated at once, batch online processing. We've got 3.6 million individual connections between the nodes here. We've got nearly 20,000 hidden nodes. And I think the final type that Dimitri shows us is something called a spiking neural network, which I've not covered. It's fairly cutting edge. Spiking updates the neurons only when there are nearby neurons being updated. Okay, so it works like the brain does. When there's electrical activity in one portion of the ANN, that portion becomes a lot more active than the remainder. And you can see this in action here, 10,000 hidden neurons with nearly 2 million connections between them. I believe that's about the end. So let's move on. So thank you very much for your time and attention. I'm going to hand over to Laura now for any questions and to talk to you a bit more about what we offer for SMEs for Segway. Thank you.
Thank you, Derek, and thanks everyone for listening. We've only got one slide left, and then we can move on to questions. So yeah, as a business at the moment, we do have some funded opportunities available for Staffordshire-based SMEs, including artificial intelligence. So if you did like what you heard today and you would like to hear more, please do get in touch. We run other courses around web-based computing, cloud computing, digital marketing, leadership. There's a whole array of courses that we're offering at the moment. So yeah, please do get in touch. Can you move on to the next slide, please, Derek? And in terms of other support that we can offer, we also have incubation and office space at really competitive rates if anyone is interested. We also look at intelligent mobility, which is a greener movement of goods and services around the world. We have funded support available for that, as well as prototyping and new product development, particularly around manufacturing. So yeah, if anyone would like to find out any more information, my email address is on this final slide. If you just move on, Derek.
Yep.
And please,
there we are.
That's brilliant. So if you do drop us an email at employers@staffs.ac.uk, we can then start advising you a little bit better about what's suited.